start playing it. Okay, so yeah, good morning, everyone. Yeah, this is my great honor to introduce today Professor Ian Horrocks. And Ian is a full professor in computer science at the University of Oxford, and is also a fellow of the Royal Society. And he was recently awarded with the Lovelace Medal for his great contribution to the knowledge representation and reasoning community, where he has been playing a key role defining the ontology language OWL, and also for his has been a key contributor in the reasoner systems Hermit and RDFox, and actually he has recently co-founded a company called Semantic Technologies here in Oxford, where RDFox is one of the key products. And the presentation will be recorded, but then he's going to be here to answer any questions. So yeah, I don't want to steal more time from you within this great presentation that is entitled Knowledge Graphs, Theory, Applications, and Challenges. And I believe that is very relevant for this neural symbolic community.
In this talk, I'm going to discuss knowledge graphs, and in particular, focus on the theory that underpins them, the challenges that need to be overcome in order to realize practical knowledge graph systems, and the kinds of applications where knowledge graphs are proving to be particularly effective. A knowledge graph consists of a set of entities and values which make up the vertices of the graph, and these are connected by labeled edges that capture relationships between pairs of entities or between entities and values. In RDF, a single such edge is called a triple. It's also interesting to note that we could store this information in a roughly equivalent way in a relational database, for example, using tables like these. However, the graph form has significant advantages. In the first place, the graph is more intuitive. The knowledge isn't split across multiple tables, and we don't need to understand hidden details of the database schema, such as foreign keys, in order to understand the structure of the data and to navigate around it. In the second place, the schema, or at least the taxonomic backbone of the schema, is explicitly represented in the graph in exactly the same way as the data. We can see, for example, that the upper part of the graph, outlined in blue here, defines the schema, while the lower part, outlined in red, corresponds to the data. Another thing to notice is that each entity occurs only once in the graph and can be arbitrarily connected to other entities. In contrast, in the tabular version of the data, the same strings occur multiple times, and string matching is used in order to make connections in the data. In fact, RDF graph entities and edge labels are uniquely identified by URIs. This has the advantage that we can directly refer to entities in other knowledge graphs and access additional information via the web. For example, we can use the Wikidata URI for architectural structure, and we could use that to access a wealth of additional information about architectural structures. Another feature of the graph data model is that it is very flexible and extensible. For example, if we decide to add information about architects, all that's required is to add the relevant additional triples to the graph. There's no need to change the table structures, and we can add arbitrarily many architects. Similarly, if the data changes, we can delete edges and entities from the graph, and the eagle-eyed amongst you may already have noticed that we need to delete at least one triple from this graph. Finally, in addition to standard retrieval queries, the graphical data model facilitates a range of other query types, including navigational queries and queries that explore structural similarities, localities, etc. Hopefully, we can all agree that so far everything looks very positive for knowledge graphs. But next, I want to consider some of the challenges that need to be overcome if knowledge graphs are going to be effective. One of the main issues is that the intuitive nature of graphical knowledge representation can obscure the fact that the semantics may be very vague and ambiguous. If we return to our running example and consider a query against the graph that asks for all of the architectural structures that are located in the EU, intuitively, given the information in the graph, which states that the UK is still in the EU, the answer should be the Eiffel Tower and the Shard. However, this intuition is based on assumptions about the semantics of type and kind of edges, as well as the semantics of combinations of location, capital of, and member of edges. Fortunately, philosophers and mathematicians have already devoted a lot of time to the consideration of this problem and have provided us with a ready-made solution: logic. In particular, we can treat the triples in the schema part of the graph as being equivalent to logical sentences of this form. And we can treat the triples in the data part of the graph as being ground facts of this form. The combination of such schema sentences and ground facts is often called a knowledge base. And we can treat a knowledge graph as being completely equivalent to such a knowledge base. This brings with it several advantages. Firstly, we can add more complex logical sentences, for example, to explicate the semantics of combinations of location, capital of, and member of edges. Second, we can also formalize the semantics of query answering as logical entailment. For example, the Eiffel Tower is in the answer to our query for architectural structures located in the EU because the relevant facts are entailed by our logical knowledge base. We can equivalently think of this as entailing additional edges in the graph as shown here. And we'll come back to this idea later when we discuss materialization-based reasoning. Finally, logic-based semantics gives us access to a wide range of existing algorithms that we can use to compute logical entailments and hence answer queries over the graph. For example, we could use natural deduction rules to deduce that the Eiffel Tower is an architectural structure. This all sounds very promising, but of course in computer science, things are rarely as straightforward as we would like them to be. In this case, the problem is that logical reasoning can be very hard or even undecidable, and this led to some early disappointments in AI research. We can't change decidability or complexity results, but we can take a more nuanced view of such results. For one thing, we should understand that these are worst-case results, and even if a given logic is undecidable or intractable, we may be able to devise algorithms that work well in typical cases. With this in mind, a great deal of research has been devoted to identifying logics that offer a good balance of expressive power and computational properties, designing empirically effective algorithms and developing highly optimized reasoning systems based on such algorithms. Description logic is a research field that is based on exactly these ideas. Description logics are a family of logic-based knowledge representation languages. They're usually decidable subsets of first-order logic and usually restricted to unary and binary predicates called concepts, or sometimes classes, and roles, or sometimes properties. Description logics are modular. There are a range of different constructors for building complex formulae, and a given description logic is defined by the set of operators supported. In fact, the strange-looking names of many description logics are simply acronyms derived from the relevant sets of supported operators. Description logic researchers have mapped out the decidability and complexity landscape for various combinations of constructors. In addition, description logic researchers have developed highly optimized implementations for various languages that seem to offer good compromises between expressive power and tractability. As I already mentioned, motivated by the idea to make web data machine readable, the W3C semantic web activity developed a range of language standards to support graph-structured knowledge representation. It was recognized that, particularly given the distributed nature of knowledge representation on the web, it would be important for these languages to have an unambiguous logic-based semantics. As we've already seen, basic RDF triples can be seen simply as ground facts, or equivalently as what is often called an A box in description logic. RDF-Ox was extended with OWL, an ontology language based on the Sroik description logic. Again, as we've already seen, an OWL ontology can be seen simply as a set of Sroik axioms, or what is often called a T-box in description logic. Finally, the W3C also developed Sparkle, a query language that is similar to SQL, but with various adaptations to suit the RDF graphical data model. The OWL language and reasoning systems proved to be very successful in ontology-centric applications, i.e. applications where the main focus is on the development of large and complex ontologies. In such applications, reasoners are typically used to identify logical inconsistencies and to compute a class hierarchy. This has proved to be very successful, particularly in areas such as medicine and the life sciences, and OWL reasoners are now routinely used in the development and maintenance of such ontologies. However, even the largest ontologies typically include fewer than 1 million classes. In contrast, in data-centric applications, such as the development of large-scale knowledge graphs, the graph can contain billions or even hundreds of billions of edges, or equivalently of facts. Moreover, the main reasoning task for such applications is not classification, but query answering, usually Sparkle query answering. Reasoners that support all of OWL don't scale well to this task. To address this issue, OWL2 introduced so-called profiles, fragments of OWL that correspond to known tractable subsets of Sroik. Not only are the profiles known to be theoretically tractable, but they also come with algorithmic techniques that are well suited to query answering. In the case of OWL-RL, we can treat the graph and ontology as sets of data log facts and rules. We can then exploit data log reasoning for query answering. In particular, we can use a forward chaining algorithm known as the chase, which exhaustively applies the rules until all consequences are materialized in the graph as implied edges. If we consider our running example knowledge graph and query, then exhaustively applying data log rules corresponding to the inclusion axioms would add type edges from Eiffel Tower and shard to architectural structure. We can now answer the query directly over the graph, or equivalently over the set of data log facts, with the answer being just those individuals that are explicitly stated to be instances of architectural structure. As we've already seen, we can use the same procedure to materialize our location rule. We could then answer a query asking for architectural structures located in France and get the Eiffel Tower as an answer. We can also materialize the rule that captures the semantics of location and member of edges. Materialization has the advantage that query answering can be very fast, as only the materialized facts need to be considered. Materialization itself can be treated as a pre-processing step, the cost of which is amortized over subsequent queries. However, materialization should still be as fast as possible. In some existing systems, for example, materialization of even moderately large graphs can take days. We also need to consider what happens if data changes. For example, when we update the asserted graph by deleting the edge that represents the UK's membership of the EU, the edge representing that the shard is located in the EU is no longer entailed. Ideally, this edge should be automatically removed, a process known as truth maintenance. However, few if any existing data log or RDF systems support truth maintenance, or at least correctly support it. In most cases, deleting edges from the graph would require the deletion of all derived edges and a repetition of the full materialization procedure. As I already mentioned, this could be very time-consuming and would make the use of such a system infeasible in a setting where the data is frequently updated. To summarize, OWL2RL seems to offer a good compromise between expressive power and scalability, and using a data log materialization-based approach could in principle allow for very efficient query answering. However, materialization can be costly, and this problem is exacerbated if the data is frequently updated. These considerations motivated our research into materialization-based reasoning and our development of the RDF-OX system. Our objective in developing RDF-OX was to support applications where the focus was on SPARQL query answering over large-scale RDF graphs, augmented with OWL2 ontologies and/or data log rules. We chose a materialization-based approach in order to support expressive ontologies and rules, while at the same time providing high-performance query answering over very large graphs. As we've discussed, materialization can be costly, so this should be highly optimized, while at the same time supporting incremental maintenance to allow for changing data. We based RDF-OX on algorithms that are not only efficient, but are provably correct with respect to the semantics. This turned out to be a critical decision, as support for RDF, OWL, and SPARQL requires complex algorithms that are almost impossible to develop via empirical software engineering. This point was illustrated by an evaluation carried out by one of our customers before they chose RDF-OX. They ran some performance and correctness tests on a number of graph database systems and found that all the other systems they tested exhibited significant failings, including timeouts, crashes, and returning wrong answers. As we've seen, materialization effectively means repeatedly answering queries corresponding to the bodies of rules and adding the answer tuples back into the graph. An RDF graph is just a set of subject, predicate, object triples, and query answering involves computing joins over these triples. To do this efficiently, we need the triples to be accessible in various orders, for example, in subject order or object order, and we also need indices that allow us to rapidly find appropriate entry points into the various orderings. Moreover, we need to update the relevant data structures as new triples are added. These considerations led us to develop novel in-memory data structures for RDF-OX. This obviously limits the size of the graph that can be stored in a single server, but careful optimization of the data structures allows for billions of triples to be stored even on a relatively modest server, and tens of billions on larger machines, which is enough for most realistic applications. RDF-OX exploits modern multi-core architectures in order to parallelize materialization. To balance the workload, each thread retrieves a new triple from the triple table, processes it using the rules and any preceding triples, and writes any resulting triples back into the table. This is in fact the well-known semi-naive algorithm. In order for this procedure to be efficiently parallelized, RDF-OX's data structures allow for updating with minimal locking. An evaluation on some standard benchmark data sets showed that RDF-OX can achieve speedups of up to 20 times on a 16-core machine with 32 threads. Finally, RDFOX implements incremental addition and retraction using a novel extension of the delete rederive algorithm known as DRED. Our first paper on RDFOX was published in 2014, and over the next few years, there were several successful industry applications of the system. For example, Kaiser Permanente used rules to capture care quality standards and to check that patient data indicated compliance with these standards. However, as researchers, we were unable to provide the support that was needed to go beyond proof of concept applications, and this led us to commercialize RDFOX via a spin-out company, Oxford Semantic Technologies, which was established in 2017. However, although RDFOX was very well engineered, it soon became obvious that there's a huge gap between a research implementation and a viable product. On the one hand, we needed to add some new features to the representation language, and on the other hand, we needed an industry strength system architecture. Regarding the representation language, one weakness of OWL is that its decidability depends on a form of tree model property, which restricts how properties can be combined. The difficulty of specifying the relationships between parent, brother, and uncle properties is a well-known example of this. However, this restriction is no longer needed in OWL-RL, and we can significantly improve the usability of the language by allowing for arbitrary non-tree-shaped rules. Another important issue is data types and values. OWL supports all of the XML schema data types, but this support extends only to allowing types and values to be used in a similar way to classes and individuals. In realistic applications, it's often necessary not only to represent data values, but to manipulate and combine them using built-in functions for subtracting numbers, concatenating strings, accessing the year in a date, and so on. Aggregation functions such as sum and average are also important. None of this is very difficult or interesting from a research point of view, but it requires a considerable amount of engineering effort. Another issue was value invention. As I already mentioned, OWL-RL and vanilla datalog don't allow for adding new nodes to the graph. However, it's often very convenient to use rules to compute new values and store them in the graph. For example, in a recipe application, we might want to use rules to add a calorie value to each recipe by summing the calories of the ingredients. We might even want to invent a new URI and to add it as a node in the graph, for example, to reify an edge in the graph. This is a little more tricky as we need to ensure that materialization doesn't add an unbounded number of nodes to the graph. This problem has already been studied, however, and suitable solutions can be found in the literature. But again, implementation requires significant engineering effort. Finally, OWL and datalog allow us to derive new information, but they don't allow us to check constraints on existing information. This is a well-known limitation of first-order logic in general. For example, going back to our recipe use case, we may want to compute the calories of a recipe only if the calories are not already explicitly given. This can be achieved by adding negation as failure to the representation language. Again, this has been well studied, for example, in non-monotonic logic, but again, it requires significant implementation effort. Regarding the system architecture, RDFOX's original system architecture was very basic and consisted of little more than the core reasoning engine, a command line interface, and a Sparkle API. We had to add numerous components, including connectors for external legacy data sources, a persistence layer that allows the graph to be stored and reloaded from disk, a web console for system operation and administration, an extended range of APIs to support applications and third-party extensions, and adaptations to allow for running the system in environments ranging from edge and mobile devices through to the cloud. We also had to add all the usual multi-user enterprise features such as access control and ACID transactions. Developing RDF-OX into the fully fledged system that we have today has taken several years. However, we are now able to support large-scale and mission-critical applications. And I want to just spend a little time looking at the range of applications that we're now seeing. These can include web-related applications such as open question and answer, as well as e-commerce applications where graphs are used to represent available products and to support searching and browsing based on product categories and features. However, many of the use cases involve industry problems that are not directly related to the web. A prominent example is configuration management. For example, RDF-OX is being used by Festo to support the configuration of large and complex factory and process automation systems. The knowledge graph includes a complete specification of Festo's extensive component catalog, along with rules that capture expert knowledge about compatibility between components. For example, a rule might capture the knowledge that a motor is compatible with a power supply only if the power supply is of the appropriate voltage and provides at least as much current as is required by the motor. Although not directly related to the web, this system is now running live on Festo's website and supports interactive product selection, configuration, and pricing. Another important use case for graph technology is data integration. An example of this use case is a project at BMW where RDF-OX is being used to integrate high-definition map data from multiple heterogeneous sources in order to support the development of autonomous vehicles. Interesting features of this application include the fact that RDF has to run on an embedded device in the vehicle and that it has to cope in real time with an ever-changing set of map data as the vehicle changes location. Efficient incremental reasoning is clearly critical in this case. Well, all that remains is to say thank you very much for listening, and I'll be happy to answer any questions that you may have.